Hello everybody, welcome to this Tech Talk. Today we're going to hear from Jake, who is going to talk about the CodeLabs matching algorithm.
Hello everybody, let me just get this shared. Okay, so hi, I'm Jake Cover. I've been a software engineering intern at SR&D for the past year. Graduated high school in June, and I'll be going to UCLA for CS this fall. So this talk will be about how I designed and implemented the backend for the student mentor matching system for CodeLabs. So that's by a couple people to give this talk, so I hope you find it informative. Also, if you go to this link right here, codeday.to/CodeLabs matching slides, you can follow along with the slides in real time on your device, and links become clickable and a couple other things that are handy, so keep that in mind if you're interested. Anyways, let's get started. So real quick, there'll be two main parts to this presentation. First, an overview of the problems that I needed to solve and some other similar problems. And then second, an in-depth explanation of what I did to solve the problems, along with a side of some algorithm design tips that you can hopefully learn from. Let's get started going over the background of what this project entailed. There was two main phases. First, there was the priorities and recommendations phase. In this phase, we used Elasticsearch, which is a tool often used to create search engines to recommend the best projects for you based on your application. I'm sure many of you remember seeing this screen if you were accepted when you chose which mentors you were interested in. We thought this approach was a good compromise of both automation and human aspects, because while Elastic was able to do a good job showing you what we believe to be the best projects for you based on the limited information we had, you were the only one who could really assess if a project's description and the mentor's bio sounds like something you'd actually be interested in working with. So therefore, we let you rank a selection of projects and then went forward using just that list to make sure you got the projects you really wanted. We think the system worked really well and helped significantly to improve the overall quality of group placements. Then in phase two was we worked on based on everyone's priorities. We needed to assign you all to projects in the most fair way we could. And in this phase, the project overlapped a little bit with more traditional matching algorithms. And so we'll go over some of those right now, and I'll point out why they didn't work in this case. So as you might know, or many of you might already know about the stable marriage problem. There's lots of interesting videos online about it. The problem consists of two groups of people, both with ordered, or really anything, two groups with ordered preferences of all members of the other group, as you can see in this picture, and then each person gives preferences for members of all groups. Well, that's you might think this works because CodeLab does the matching is two groups, students and mentors. Only the students have priorities, so this system won't actually work for us. The next problem we took a look at was the stable roommates problem. It has only one group with priorities, so that's better. It's for matching roommates to other roommates if you're like a college or something. But it doesn't require preferences for all members, which is good because the students only put in votes for a couple mentors, not for all of the mentors like is required for stable marriage. However, the priorities for the group members are for members of the same group, if that makes sense, not for another group. So this one also doesn't work. The reason I wanted to look into these two problems is because I know that they have mathematically optimal solutions that I've been able to find online, which would have been very convenient. But like I mentioned, neither of these particularly fit to our problem. And despite more research, we were not able to find a problem that mapped well into what we needed. There's lots of these problems available, and if you're doing something similar, I'd strongly recommend to take a look at these, because if you can find the solution that works, it's very helpful. But in this case, we weren't able to. But also, where's the fun in using someone else's algorithm? That's basically cheating. So now onto the nitty-gritty of how I solved the problem we just outlined, and I hope to give you some guidance on how to do something similar in the future. There's going to be a few parts starting from the beginning and moving through all the components that were involved. So the first part was data collection. This started with the student and mentor applications, where data went into a Cognito form and came out as a very poorly formatted CSV. That required an extra step to turn the data from what Cognito gave us and into something that would actually work with Python. I was really disappointed that Cognito didn't have a good solution to export to JSON. There's a way you can do it, but it only works as answers are streaming in, so it's really not particularly useful. We ended up with the data that you can see in these schemas here. We chose information that we believed would be relevant to the success of the team, like time zone information to make sure everyone's in a similar time zone, the companies that students were interested in and the interests that they had, like web and mobile, UI, UX, the other things that we mentioned earlier. This required a little bit of human effort to normalize some fields, but that could have been worked out better had we had planned better. All in all, this part went really well. I think Cognitoforms is a good tool for this. I just wish they had a better export tool. An important note on this, though, none of this was involved in accepting or denying applications. That was all entirely manually reviewed because we did not think we could build a good enough system to review applications well enough automatically. So now I'm about to go in depth about some of the details of Elastic and its Python tooling. I'll use a few examples that are at the other end of that QR code right here, so you can follow along there if you'd like. It's also a general example of the Elasticsearch Dsl Python library if you're doing something similar, which I'll talk about in a minute. So if you're interested in following along there, you can scan that QR code on your phone. It'll also be on the next couple slides. So in my opinion, Elastic, which is that search engine tool I mentioned earlier, is great, but also sort of the worst thing. I have a number of gripes with it that I'll go over in a minute, but the biggest problem that I found is the docs just feel really bad. Like they're kind of from another era where programming books were the requirement to learn pretty much anything. The biggest problem is that while they are in depth and they do cover almost all of what Elastic does as docs are supposed to, they lack good starting explanations and beginner things. And in general, it's very difficult to get started. And it's also very hard to get to a point where the docs are actually understandable and usable. As a counterexample, I don't know if any of you have used Google APIs or the Android documentation. In those places, there are tons of examples all over the place with superb quick starts and a couple other things that make getting started very easy. And I wish Elastic had things like this. It would make getting started with it significantly easier. Next, the Python tooling kind of exacerbates some of the problems that Elastic has by itself. So there are three main ways to get started using Elastic and Python. First is request.py and use it to send queries in JSON. This is likely to be problematic because essentially you're just making web requests with JSON data attached. This means that there's no helpers for connections or connection pooling or anything like that. And it leaves you doing a lot of string formatting, which is very error prone at this scale. And it's also very difficult to make multiple query designs for different student types, which is a thing I'll show an example for in a second that I found very powerful with one of the later tools. Next, there is the Elasticsearch Pi Library, which is better than requests because it handles authentication, connections, and other things like that well. But it still requires you to use string formatting to create JSON queries. If you're not familiar with string formatting, that's what's required to take a string and add another something inside the string, like to append two strings or to insert a variable into the middle of a string. And while it's really handy in a lot of cases, it's not the best way to do something that's complicated because lots of things can get lost. And then also these two approaches are very vulnerable to injection attacks, which may be a concern for you. In this case, I'll get to it in a second, but there's a way that we were able to get around having to worry about that, which was very convenient. But finally, and this is the tool I went with, Elasticsearch Dsl, which is a higher level library for Python that aims to help more with queries. It seemed to be the best solution at the time, and I think it still probably is, but it has even worse documentation issues that I'll get to in a moment. And yeah. So the core feature of the DSL is the usage of this Q parentheses syntax, which you can see here in a couple examples. This is it's a way to represent a query, but it has a couple issues with it that I really think are pretty problematic. So first is the way it represents what type of query. It requires you to pick to use the name of the query as a string. The issue is these names come from the Elastic documentation, not from the documentation for this library, and it's difficult to find exactly what all your options are. The first example here shows how Q syntax works very well. What you can see is all this code block basically creates a compound query for all of the companies that students said they were interested in. I'm not sure if you remember, but in the application, you were able to put a list of as many companies as you wanted to that you thought you would be interested in. And we basically built it so that it fuzzy matches each of those companies to avoid errors with spelling or anything, and then gives a total score sum. So for each mentor, you would get, like for each mentor, right, they each work at one company. So if you put that company down and the fuzzy match worked out to be true, you would get a boost to that mentor, so it would appear higher in your list. And this was able to do it with one query for all the mentors, which helped a lot with performance. The second example shows one of the pain points. Here you'll see something that's labeled SF instead of Q. That stands for score function, which is something from the Elastic docs, but it is only used in this one particular case with the function score query. And because the docs for the Elasticsearch Dsl library didn't go into good detail for each query, there was no way to actually discover easily that this SF function existed, which meant I had to spend an hour or so looking around trying to figure out what went into the functions field for this query. And I eventually found it on Stack Overflow, which was rather frustrating because it should have been on the documentation somewhere. And then finally, the scripts. It's a great idea. It allows you to design your own queries if Elastic doesn't have one for you, which I used a couple times. But the problem is it becomes very frustrating in practice as debugging becomes very difficult. It uses a DSL called Painless, which is basically Java, but with some differences, but it's really anything but. My first gripe is that all the code is written in strings. Yes, as you can see here, it's literally, as you can see here, come on. As you can see here, the code is literally written inside this string. It's essentially like using Notepad to write Java. And also as a Python developer, I don't really know Java all that well, so that was an extra problem here. I'm not really sure what else they could have done because this needs to somehow fit into a query that's going across the web, but I feel like they could have made some tool to make this significantly easier. This actually goes on for a while here. As you can see, it's not like that long. It probably should have taken me 20 or 30 minutes in Python, but it ended up taking me a good few hours to get this working because the debugging was problematic. Essentially, the only way to do debugging is using these functions that return the type of a variable, but there's another issue with that I'll get to in a second that makes that difficult. The code and string problems also mean that there's very little readability on the actual code. It's very hard to tell what's going on. But then it also makes debugging a problem. So with the Python DSL library that I'm using, when a script has an error, it doesn't return a useful traceback or anything. It just says if it was a compile error or a runtime error. And I guess that's better than it just saying that it errored, but it's really not particularly useful. So I figured out that the only way to get this to actually work the way you want is to force it to load up or to translate your query into JSON like you would use with the other two libraries, which can be difficult in some cases with some of the harder and more complicated parts of your query, and then use Perl or Postman, which is like a tool to basically do web requests with a good GUI. And then you will then get a traceback from there. But that means you have to translate your thing from your Q syntax to JSON and back, and that's really frustrating and difficult at times. Essentially, it also broke the explain function. That's a pretty minor complaint that I don't really need to cover. You'll see when you do it. But essentially, the Q syntax, it's a good idea. It has problems, and I really wish they had done it better. But what's my point with all this? So as much as I've been complaining about Elastic, it's incredibly powerful. You can't do search well in Postgres or MySQL. I've definitely tried, and it just doesn't work. So they're trying to fill an incredibly difficult problem space of just like search as a general idea. And when everything finally works, it works really well. And I will admit, complexity is inevitable in something this general and powerful, but bad docs aren't inevitable, and they really could do something about that. But for the time being, you should probably just buy one of the books I mentioned earlier and start with another project before you move on to this one, or whatever big algorithm project you're planning on. So APIs are much easier than Elastic was. I chose to go with Flask since it's very easy to make a simple API using it. There's a million tutorials for this, but if you know anything about Flask, you can make a simple API really easily. Here you can see the code for an API endpoint. It's literally 12 lines. The whole Flask app was 100 lines for the 3 endpoints I needed. Flask at times can be somewhat temperamental, so here's a couple solutions for some problems that I found that I hope you can make use of. So Python imports can be weird, especially when you have an unusual directory structure and Docker containers. If you've ran into this problem before, I think you'll know what I'm talking about. This code here is very helpful. What it does is it adds the current directory of the directory that the script is in to the Python path, which basically means you don't have to do relative imports or imports from a different folder. And all that means is that if you're Dockerizing your Python script, this will make sure it works exactly the same, no matter how it's being run on your computer or on the Docker container, which was very helpful for me because I was having a few issues with that. And then finally, the other piece of information I want to mention is that this very useful bit of code here. Essentially, if you've ever used Flask before, you'll know that it has the application context, the app variable, the app object that is really important for everything. And so sometimes you want to import that from a certain file, and you can get caught up in circular import errors. I have always been fighting that for the whole time I've used Flask for a couple of years, but during this project, I learned about this current app import, which is a totally safe way to import the application context from wherever you, into wherever you want without having to load up the main script and cause a circular reference error. It's incredibly helpful. Also, something that builds on that is the ability to store any object you want onto the application context, which I found incredibly helpful. This might not make much sense if you haven't used Flask before, but once you get started, at the end I'll have a link to this presentation online, and so if you get started with Flask, you can take a look at this then and see, and hopefully it'll be useful. And then the final key to Flask and all of this stuff was Json Web Tokens, which is essentially a way to sign JSON data to verify that it came from the correct source and get it ready to be sent over the web all in one stroke. I essentially used it to validate that data came from the correct source, which in this case was Tyler's API, or Tyler's web UI that I showed earlier in a screenshot. It's very easy to use. I recommend the PyJWT library if you're building something in Python, not one of the more complicated and Flask-specific implementations. I thought that those just were hard to set up more so than they needed to be. Here's a simple GET request, or like data that would be sent to my API through a GET request, and then here's what it looks like encoded with JWT. Essentially, when you decode that, it will return the information on the left, but it will also verify that it was encoded with a certain string, and you can check that the key that was used to encode it is correct. And if it is, that means you know that the data came from a trusted source, or at least the place the data came from knew the secret key, which is as good as knowing it's a trusted source. Hopefully this is helpful if you're ever doing something API related. In case you're curious, here's what my plan for the final placement algorithm looked like. However, this is absolutely illegible on a slide and also mostly unimportant. So we're going to talk about what is important from this information here that you can hopefully take if you're working on something like this. So first, there are multiple steps. As you can see, there's 4 steps here. It's important to remember that when you're coding something, you're not really beholden to much at all. And so you can keep in mind that you can take as many passes as you want over your data. In this case, I took 4 passes, as you can see here, each time eliminating a certain amount of the students from the data set, which was very helpful. Second, you can see the descriptions are very clear in their intention. If you try and read the first one, maybe, you can see is that it's very technical and specific, and that helps. That means that when you're actually implementing it, you'll have less problems. And if you have a problem while you're implementing your plan, you'll probably have to change from the plan, and I'll get to why that's important in a second. And third, something will inevitably go wrong. No plan can be perfect, especially with something complicated like this. So make sure to build in, or I think it's a good idea to build in checks and metrics so you can verify that your algorithm actually worked as intended. And even if you design these correctly or very well, you can make sure that they get removed if it's really performance critical, if your API is or if your algorithm is very performance critical. So how can you go about designing an algorithm like that? My process has a few key steps, and I think hopefully that you can learn from these and use these in your own projects. First, start with planning. It does not matter if your first plan is very good, just come up with something that you think can solve the problem. Then if you want to, then you definitely want to try to break your approach. You might want to spend a couple minutes thinking through edge cases and trying to solve any issues that show up. Then you definitely want to repeat this a couple times. If you find out that your plan doesn't work during the first pass, you might need to start over and come up with a totally different plan. I know the plan that I showed earlier, that was 3 restarts and then like 4 revisions of tuning. And while you might want to get started as soon as possible, that's never really a good idea with something this complicated. If you can fix something before you spend 4 hours coding yourself into a corner, you definitely should. Also, those are words to live by. So once you're pretty confident in your plan, you can start implementing it. if you made a good plan, this should definitely be the easiest part so far. And there's really not a whole lot to say about this. In whatever language you're doing it in, with whatever tools, just write what you planned out. But inevitably, something will go wrong and you'll need to patch it out or patch up some problem. This happened to me and it'll probably happen to you. So you want to make sure that you step back and really analyze your issue to make sure that you actually find the root cause and not just some superficial part. In my project, I was losing students, as in they did not get placed into any project at the end of the process. So I realized there was a flaw in how I was originally allocating students and needed to change how that worked in order to make sure that I got as many students allocated as possible. Finally, you might want to consider creating some metrics so you can easily fine-tune the results. In any algorithm, there's probably 5 to 10 different variables that can be tweaked to change its performance in a couple different ways. And you want to make sure you have metrics so you can know how what's happening when you're tuning it. So as I mentioned earlier, I had the metric of keeping track of lost students, so I could make sure to minimize that, or preferably get it to 0. But then I also created a metric to see the average choice number that students got, which means it's the average, like on average, what place did students get if you were to average all of their eventual placements. It averaged around 1.52, which I thought was really good, meaning on average, a student in labs got either their first or their second place vote in general, which I thought was very good. This number was also useful as I could see that as I lowered the number of students getting lost, the average choice number went up, which was interesting to note. And also I was able to tell that the first time I ran this metric, I was able to see that I actually overshot on patching and I could improve the student score metric a little bit while and without any change in lost students, which was very good. Finally, you need to know when to be done with your algorithm and if your remaining issues are actually solvable. No matter what I did, I could not get the number of lost students below 5. And it turned out that it was actually inevitable with the way the choices were distributed relative to other students' choices. So I had to give up on tuning the algorithm and work with the rest of the labs team to move on to the final phase, which was manual cleanup. You may be asking, is the whole point of building the whole thing you just built to avoid manual cleanup or manual effort at all? And you'd be totally right. That's the point of the algorithm, right? Is to automate some task that was originally complicated. However, sometimes it is the fastest way to finish up, and as diminishing returns might have taken over your development process, as they did with mine, I would have had to have implemented some very complicated solution to patch out the 5 students that were lost at the end. So instead, we decided to place them manually. It's important to note that in your particular use case, this might also not be possible. If your algorithm is somehow required to fit into an API, like the Elastic part was, if it needs to be automated or just ran frequently, you might need to put some sort of conclusion. For example, on this, if I had a lot more time and I could have queried Elastic for that student and then for the lost students and then use that as a backup set of votes that were better than randomly placing them. But again, it wasn't worth it in this particular case. And for how to actually do manual cleanup, there's really not much to this step. You just need to decide how to place edge cases. It's really helpful to have other people to work with on this. Lots of the CodeLabs people mostly handled this step, which was very great. But multiple people means that you can have other people check your work, which is especially important if you're moving people around a lot. It's really helpful to have other people check to make sure that you didn't cause some cascading problem of overbooking or underbooking or anything like that. Finally, I'll end on a speed round recap for the technologies and tools that we're using in this project so you can make an educated decision on what to do next in your algorithm design project. First is Cognitoforms, which allows you to make really great web forms that can be embedded and themed, but they really need to get data export right. JSON is really important for this kind of thing. Elastic does a very complicated job pretty well, but its tooling and docs make it very frustrating to use. I haven't used any of the other offerings in the search and weighted results sphere, so I can't really compare them to Elastic, but I've seen things about Elastic Solar, S-O-L-R, that seem interesting, so maybe take a look at that if you're trying to do something that involves fuzzy matching or weights. Python is amazing for something like this. It has this feature called list comprehension that I'm not really sure if other languages have, but in Python, it's incredibly powerful. It essentially allows you to iterate over lists in one line, but you can also use if statements to filter lists. You can nest them, and you can even generate dictionaries with them, which allows you to take a 20 or 30 line, really ugly and complicated piece of logic that iterates over a list and turn it into something that works faster and is a lot neater. And in general, it's just like a much better way to solve the problems. It's incredibly powerful, and I strongly recommend looking into it. Additionally, for algorithm things, they're mostly ran on servers or in that kind of environment, and Python runs excellently there, much better than it does on like an individual computer. So it's excellent in that way as well. Flask is a pretty great web framework for APIs. It's not too opinionated like some other Python web frameworks, so it's really easy to make something simple like I did. It still can have odd problems like I mentioned, and it can be generally confusing to start with at times, but once you know how it works, it's really great. And then finally, JWT is a fantastic way to confirm that JSON data came from the right place online. It's 10 out of 10. You can look at jwt.io to find more information about that if you're interested. So with that, thanks for coming to my talk. I saw I got some questions, so I'll answer those in a moment. If you have any questions later, feel free to reach out to me. I'm one of those places on the left. And you can find the slides on my GitHub at the presentations repo you can see right here, if you want to look at that again. Also, CodeDay is pretty great. I know most of you from labs are probably heard about this already, but in August, we'll be putting on the next virtual CodeDay, which is a totally free and online event where you can work with a team to make a game or an app. So if you've learned things at labs and you're interested in maybe working with your labs team again, definitely check codeday.org for dates on that. Thank you. And now let's see, let me take a look at these Q&A questions. So someone asked, what in your opinion makes good docs or bad docs? So yeah, if you're writing documentation, is definitely an important question to answer. I think one of the most important parts about documentation is getting people started with your project. It's all too easy when you're writing documentation to just auto-document the main part of the code base. And so if someone who knows what they're doing wants to figure out what a function call does, they can definitely check that out. But what makes docs really good is having lots of examples to show how things are really work in practice, and getting started information so people can get up to speed quickly. If you build something that's big enough, like kind of like Elastic is, you can kind of trust the community to do things like that, but it's never as good if you do it yourself. So if you're making documentation and want to make it good, I strongly recommend getting started information and examples. As far as factors that were weighted higher than others in the algorithm, the biggest factor that was weighted the highest was if your tags that you said you're interested in matched with the mentor's tags. With that, and then actually, some students had to require an extended internship, which meant that they had to have an internship that was longer than labs, just for some reason, like maybe a school requirement or something. So if you had an extended internship, you were only showed mentors that were okay doing an extended internship. And if you didn't need an extended internship, I believe you were still shown them, but they were given priority just because they had to be, because they needed that. But like I mentioned just a second ago, the most highly weighted part in the algorithm was, I believe it was, yes, it was the tags. So if you said you were interested in web design, we would make sure that we recommended to you web design projects. One problem that came up is that a couple students just picked all the tags, maybe because they thought that would help them game the entrance system or something. But that actually severely messed up the recommendations, and which was kind of unfortunate, but there wasn't much we could really do about that. But yeah, the highest weighted factor was definitely the interest tags. Let's see here. So if you have any more questions, feel free to ask as well. Someone just asked, what do we need JWT for? So essentially, yeah, this was designed to be, essentially we put it in because I wasn't sure exactly where this would end up going. I wasn't sure if it would be, the HTML would be generated internally and then sent out by the UI that you saw, by like the web server that runs that, or if the requests would come from your client. And so we wanted to put some amount of security on it like that. I think it's, but I think this kind of security is always important. I know for a fact that this was supposed to be just LAN, or just inside our like virtual LAN in the cloud. But I actually set up the traffic configuration wrong. And essentially it was actually exposed to the internet for a while there. And so it was actually good that I had this security on it. Since JWT is so easy to implement, let me pull up the slide that I mentioned. Let's see, I mentioned JWT on real fast. I don't have the code sample of, oh wait, no, it's this one here. As you can see, JWT is lines 3 through 6. That is all of the stuff that it takes to actually verify that a piece of incoming data was signed with the correct key. So again, it takes almost no time to implement, and security is good in case someone, like you mentioned, in case someone hacks into our cloud, since this is PII or personally identifiable information, this can't be leaked, but also in general, it's just very useful to have this kind of layer on there in case something is done wrong by accident.
All right, well, it looks like that's all the questions we have for today.
Yeah, so everyone, thank you for coming. I'm really glad I could present this and hopefully help some of you out on some of your projects.
Yes, thank you, Jake, for this amazing presentation, and thank you to all the attendees for all the questions they asked. Thank you, everybody. Have a good evening.
Thank you, bye.